Okay. All right. Um, so it's a great pleasure to have Andrew Wilson be our speaker for the Amy seminar series today. Andrew Gordon Wilson is a professor at the Courant Institute of Mathematical Sciences and Center for Data Science at New York University, and an Amazon scholar. He aims to develop a prescriptive foundation for intelligent systems. His work includes generalization theory, Bayesian inference, equivariances, time series forecasting, and scientific applications, particularly in computational biology, physics, and materials. He has received an SF Career Award, Hale Brun Distinguished Fellowship, Amazon Research Award, and several best paper, dissertation reviewer, etc. I got to know Andrew while he was uh, at Cornell for a little while, and I got to learn about Bayesian inference and Gaussian process actually from Andrew. So the one paper we wrote together was actually very impactful for um, expanding my knowledge base and learning about new approaches. So I'm really excited to have Andrew. Without further ado, Andrew, please take away. How about let's make it like 15-minute presentation, and then we will switch over to question and discussions. All right?
Sounds great. It's really nice to be here. I was at Cornell just long enough to brainwash everyone into being Bayesian, and so it's a pity I'm not there in person. I'd love to know whether that's stuck. I imagine there are a few Bayesians in the audience right now, and in fact, the word epiplexity was loosely inspired by Bayesian thinking. There's something called epistemic uncertainty in Bayesian inference, which is uncertainty associated due to lack of information, and epiplexity is really about trying to capture structural information that we can teach our models from data. So this is work done in collaboration with Mark, Shikai, Yiding, Pavel, and Zico. And we'll start with a warm-up question. So if I showed you this image, would you say that it's noise? I assume that unless you stare at it for a very, very, very long time, you would probably say yes. It could be like one of these modern pieces of artwork where eventually a face or something like that sort of comes out at you. And in fact, I did quite subtly, perhaps too subtly, bury the word epiplexity in this white noise. And this was to make the point that whether or not something appears random depends on how much computation we have. So in this instance, how long we're kind of willing to stare at this image. And this was really a key consideration when we were thinking about epiplexity, which is designed to help us reason about what information data can actually teach our models towards downstream generalization. This is also a really important consideration in cryptography, in thinking about things like cryptographically secure pseudo-random number generators. Pseudo-random numbers are indistinguishable from actual random numbers if we only have polynomial time computation. So whether or not something appears to have structure depends on the observer and how much computation is available to them. We were also really motivated by what we presented in this paper as three apparent paradoxes in information theory. So these are statements that can be justified mathematically, but our intention with empirical results increasingly, as well as some intuition. So the first of these is that information can't be increased by deterministic processes. So there's something called the data processing inequality, for instance, in classical Shannon information theory, which says just this. And there's something similar, information non-increase, in algorithmic information theory, and we'll review that in a little bit more detail in a moment. Yet, synthetic data, which is deterministically generated, is very useful, and pseudo-random numbers are deterministically generated, and they're ubiquitous and very useful. And we have these systems like AlphaZero, which have short description lengths, but actually can teach our models something very useful. So what's going on there? There seems to be a tension. The second paradox is that information is independent of factorization order, so ordering of data, for instance. So this comes from Shannon's symmetry of information. There's something similar in algorithmic information theory with Kolmogorov complexity. Yet we know LLMs, for example, are going to learn a lot more from English text ordered left to right than in some arbitrary ordering. In a lot of data, there's some arrow of time which seems to convey useful information that can teach our model something. And finally, likelihood modeling is merely distribution matching. So in expectation, the best that we can do if we're doing likelihood modeling is to just find the generative process that created our data. But we often see models going beyond those processes, for example, with emergent phenomena. And I would say AlphaZero is another good example of that. And so it's our contention that these paradoxes arise because information theory and learning theory assume unlimited computation and they fail to target useful information content. And so we'll introduce this measure of information, epiplexity, to shed light on these paradoxes. And this will involve reasoning about computation and targeting specific types of information. So just to expand on this a little bit, we couldn't imagine this system like AlphaZero, which can be stored using a very small amount of memory. So we have the rules of chess, which is just a few hundred bytes, training algorithm, probably about 10 kilobytes, seed, just 32 bytes for randomness. And in total, we wouldn't expect to have much more than about 12 kilobytes for the description length of this system. So since information can't be created from things like the data processing inequality, what is AlphaZero actually learning in this procedure? It seems to lead us to a system which can play games much better than people can. Okay, so as I mentioned, we introduce epiplexity, which stands for epistemic complexity, to help us understand these phenomena and to provide a foundation for reasoning about data selection as opposed to model selection. So quite often in machine learning theory, we're assuming that we have data that are drawn from some particular distribution, and then we want to select a model which is going to make the best predictions on withheld points from that distribution. And so there are principles like Occam's razor that come out of that. And that's something that actually is encapsulated in doing Bayesian inference and has been featured in some of the work I've done with and collaborators. But in this talk and in the Epiplexity paper, we're now considering the question of data selection. And this actually can lead us to quite different principles. Maybe from the perspective of data selection, we actually don't want simplicity. We want a certain type of complexity that's going to teach our model useful information that could then lead to good downstream generalization in a variety of settings. So you could imagine that if you are able to learn shared circuits and subprograms, you can recycle that structure in many different settings. And this has relevance beyond the specific distribution that you're training on. And so we'll unpack a lot of this a bit later in the talk. First of all, we'll just take a step back, now talk a little bit more about the difference between structural information content and random information, and then we'll also talk a bit about classical information theory, algorithmic information theory, and some related concepts before diving deeper into epiplexity. So in this figure here, we have three rows which are showing different amounts of what I'm calling random information and structural information. So in the first row, first column, we have just some simple repetitive code. In the middle column, we have a simple gradient of color. And so this data is very compressible. It doesn't really contain much structural information that would teach our model something very interesting. It also doesn't contain much noise, not much random information. And as we'll see in a moment, epiplexity can heuristically be measured as the area under the training loss curve above the final value of the loss. So this data is very learnable. The loss shoots down very quickly. But there's not going to be a big area once we subtract above the final value of the loss here. So we have low epiplexity and low randomness, and we call the remaining component the time-bounded entropy. In the middle row here, we have some structured code, some natural images. Here we have information which is going to be useful for training our model and making downstream predictions. So we have a reasonable amount of structural information content, epiplexity. We have a moderate amount of random information as well. In the bottom row, we just have random hashes we have to basically memorize. This is totally unpredictable code. In the middle column, we have white noise, and that is going to be very incompressible, but it's not going to teach our model anything useful. And so that's random information, not structural information. And whether or not something appears random depends on our computational resources, and that will be important when we're defining epiplexity. So just stepping back a bit, we can reflect on really what we mean by information. There are many different measures and theories. There's classical Shannon information theory, where information is the surprisal in seeing the value of a random variable. There's algorithmic information theory, which also applies to non-random variables. It's often focused on the compressibility of data measured by something called Kolmogorov complexity. Intuitively, useful information ought to reduce our uncertainty in predictions. And so there are all sorts of systems involving pseudo-random numbers and synthetic data, things like AlphaZero and well beyond, which seem to be teaching our model something, but classical information theory would say that it's not teaching it information. So what is our model actually learning? Okay, so just in a little bit more detail, for Shannon information, we're concerned with random variables, capital X, drawn from some distribution P of X. The Shannon information of an outcome drawn from this distribution is log base 2 of 1 over P of X measured in bits. It's often said to be the surprisal in observing X. So if we see a sample that has low density under that distribution, we're very surprised and we gain a lot of information. The Shannon entropy measures the average information content in our random variable X. And the mutual information is our uncertainty in X after we observe Y, our uncertainty reduction in X after we observe Y, or our uncertainty reduction in Y after we observe X. There are several key properties of Shannon entropy. So we have the symmetry of information. The amount of information that we gain in predicting X from Y is the same as what we would get in predicting Y from X. Deterministic transformations don't add information. So if we have a transformation f of x, f, which is deterministic, giving us y, then the entropy of y given x is 0. And as a corollary, the entropy of f of x is always less than or equal to the entropy of x. And we have the data processing inequality. If y is obtained through x through some processing, like a deterministic transformation or otherwise, and similarly z through y, then the mutual information between x and z is less than or equal to the mutual information between x and y. And this has often been used to debate about things like what happens when the internet is all AI slop and LLMs are trained on that slop. Are they actually learning anything? I mean, this is a debate worth having, but I don't think the data processing inequality has much bearing on it. So in Shannon information theory, objects which are not random must contain no information. Algorithmic information theory studies the information content of an object X, which doesn't need to be random. Central to algorithmic information theory is prefix Kolmogorov complexity, which is the shortest self-delimiting program that outputs X and then halts. So this is really, how compressible our program is in principle. We don't know what the shortest program is, so this is going to be incomputable, but we can easily upper bound it, like the compressed file size of our model after training, for instance. And that upper bound is often quite useful for formulating things like generalization bounds and just reasoning about the properties of what we might have learned. There are similar properties of Kolmogorov complexity as for Shannon entropy. So there's a symmetry of information, and there's also an information non-increase property. And like Shannon information, this is an absolute measure of information, and it doesn't separate useful from unpredictable random structure. There's a somewhat more advanced concept in algorithmic information theory called sophistication. And so sophistication is the smallest Kolmogorov complexity of a set S such that X is a random element from the set. This does try to carve out a difference between structural and random information, but unfortunately it's difficult to find high sophistication objects due to something called Chaitin's incompleteness theorem. You can show that it's impossible to prove that your Kolmogorov complexity is greater than some amount. And owing to unbounded computation, complex objects often appear to lose their complexity when measured by sophistication, and it's hard to simply make sophistication time-bounded. So in the paper, we show this becomes essentially constant for all strings. And as I've been saying, we think that understanding the role of computation is really central to understanding generalization phenomena in AI and beyond. There is a compute limited notion of Kolmogorov complexity called Levin complexity. So it's concerned with how compactly you can generate a specific output rather than what can be extracted from a distribution. So a bit different than what we have in mind for epiplexity, as we'll see. Pseudo-random numbers are actually treated as simple from the perspective of Levin complexity because there is a short program that will generate pseudo-random numbers, even though they ought to be fairly incompressible in practice. And Levin complexity doesn't distinguish between unpredictable and predictable structure. Okay, we can also step back and think about what really is random. So a random variable formally defines a map from a measurable probability space to different outcomes with probabilities corresponding to the measure of the space that lead to a certain outcome. In the mid-20th century, mathematicians were really interested in formalizing what it means for a sample to be a random draw from a given distribution, and they were often considering uniformly sampled binary sequences from which other distributions can be constructed. There was a key consideration around whether if all sequences are equally random, are they all equally are all sequences equally random since they are all equally likely. So we could consider, say, just a string of ones versus, something like 100111101. Is the first string as random as the second? It has the same density, so in some sense it seems like yes. But we could compute statistics of these sequences. We could look at things like the law of large numbers, which would say that the average entry of the sequence should be a half, which clearly doesn't apply to the first string of ones here. And so Martin-Loif randomness tries to formalize this intuition and says that a sequence has to pass all computable tests. And this can also make use of Kolmogorov complexity. And so the 111 sequence, for example, is very compressible, and it's in this sense, kind of intuitively feels less random. There's also a notion of cryptographic randomness, where sequences must pass all polynomial time randomness tests. Okay, so in cryptography, they have thought a fair bit about computational constraints, unlike in information theory and learning theory. So cryptographically secure pseudo-random number generators will generate sequences which are statistically indistinguishable from actual random numbers if you have only polynomial time computation. There's a closely related concept in cryptography called a one-way function, which we make use of in our experiments, which are very computationally efficient to evaluate in one direction, but really computationally expensive to invert. So we can look at the outputs of pseudo-random number generators and show that they don't increase Shannon information by the data processing inequality. And they also are not significantly changing Kolmogorov complexity. And so how can it be that these numbers are practically indistinguishable from actual random numbers, but don't add information? We also consider elementary cellular automata to reason about the role of computation and emergent structure and deterministic transformations in a number of our experiments. So just as a bit of background, ECA for short are a 1D array of binary cells. So like the cells can each take values of 0 or 1. And each cell's next state at the next time step depends only on its current state and the states of its two neighbors. And so this means we have 8 possible local neighborhoods, 2 cubed, 111, 110, 101, and so on. And we can assign a rule to each of these local neighborhoods for describing the evolution of the state of our cell. And so that means we have 2 to the 8 or 256 different possible rules. And these rules give rise to quite an array of different structures. So in the far left panel here, we're just showing an example of rule 30. So 111 gets mapped to 0, 110 to 0, and so on. In these figures here, we have time evolution running from top to bottom. So in the first row, we have like our first set of states, just a binary sequence. And then we update it based on, in this instance, rule 15 in this left panel here. In the middle panel, we use a different rule, rule 54, and we can see that there's a lot more sophisticated structure here. Rule 30 is almost like a pseudo-random number generator. So it creates structure, but it's fairly unpredictable. We also have imposed these images of coffee and cream on top of each of these rules. So some of this work was partly inspired by a blog post from Scott Aronson called something about like complexodynamics. And he's considering the system of coffee and cream, which are initially separated, and then you start mixing them together. And he says that as you proceed, the entropy of this system is going to just keep increasing. But intuitively, the sophistication of the system is non-monotonic. So we start in a state of low sophistication, and then that increases in one of the intermediate states where we have a lot of structure, but it's still predictable. And then at the end, we just have basically randomness and we don't have very much sophistication. There's nothing we can really extract from that system anymore. So we've covered a fair bit of motivation, including these paradoxes. Another motivation for Epiplexity resulted from several projects that we had in our group where we found that language data was surprisingly transferable to other settings. And so we had a paper where we just took a pre-trained next word predictor off the shelf without updating its parameters at all and then applied it to time series forecasting, just naively representing numbers as strings. And we found that it could, in many instances, work better than purpose-built time series models that had actually been trained on this time series data that we're trying to predict. So the LLM here was at a huge disadvantage. Not only was it trained on a completely different modality of data, it was doing this completely in a zero-shot setting. So we weren't updating its parameters based on time series data or training data from these time series that we were trying to predict at testing. And so this was quite interesting. Why was it the case that this next word prediction task transferred so well onto a completely different modality and a seemingly quite different type of problem? Because we were even just naively representing the numbers as strings. So 411 might be closer to 911 than 412 from the perspective of the LLM, but this seemed to work. We found something similar with materials. So we had an LLM generating stable inorganic crystals with various desirable properties. And in this case, we had the text pre-trained model, and then we fine-tune it on atomistic data represented as text, so locations of atoms and energy levels and so on. And then we would have it generate crystal structures. And this worked really well. And I mentioned this in a talk I gave at Flatiron some time ago, about a year ago. And someone came up to me afterwards and said, we read your paper and we actually found out how to get rid of the fine tuning. So it's just text-based pre-training and we can get comparable results. And so this was very surprising. In both of these papers, we tried to provide some understanding of what's going on. So it did seem like language was teaching the model some notion of Occam's razor, and it was learning how to quickly recognize things like rotational invariances and so on in the crystal generation problem. But, still, why? Like we can say, okay, this, is being taught to the model, but why is it that language seems to be special, like that it's transferring onto these other modalities, but not other types of data like images? This is also starting to be noticed for something called neural cellular automata. So that's related to the ECA that I described, but you just have a slightly different procedure for generating the evolution of data. And this seems to be useful as pre-training for quite a variety of different problems like text code and math. So the question is, why? All right, so with all of that motivation, we can now formally introduce epiplexity. So epiplexity is the size of the model that minimizes the two-part MDL representation of data when searching over a space of normalized, probabilistic, time-constrained models. And so the two-part MDL for data don't worry if this looks intimidating. It's actually not that complicated. The two-part MDL for data is the model bits, how many bits it takes to store your model, plus the data given the model bits. And so that's the second part here. And this second part is like a cross entropy loss term. Capital X here is a random variable, and that's representing our whole data set. And so first, we find the best compression of the data that we're considering under a space of normalizable, discrete probability models. And then we measure the model bits associated with that model, and that is the epiplexity. And the remaining part we call the time-bounded entropy. So that's what's still kind of unpredictable from the perspective of the model. We can heuristically approximate the epiplexity by measuring the area under the training loss curve above the final value of the loss. And so we can go into this in more detail perhaps at the end if there's interest. But this is related to an old idea in information theory called frequential coding, which basically um, gives you a code length for a model from training on data without explicitly trying to, say, compress the parameters of that model. So it's based more on the dynamics of training. And so if you have, for example, a sustained and substantial decrease in training loss, that would imply that a lot of information has been transferred from the data to the model. We actually proposed also a new measure of compression called frequential coding. And so this is like an expected KL divergence between a teacher model and a student model. So it can be visualized as like this red sort of area here between these curves. And so this essentially works by not needing to account for the entropy of the data when you do the compression. And this allows you to have much tighter code lengths, and it's related to something called relative entropy coding, but still somewhat different. And so these are two kind of simple ways that we can approximate epiplexity. Okay, so now that we've introduced epiplexity and we have a way of measuring it, we can use it to shed light on some of what we had discussed earlier. So if we have samples from a pseudo-random number generator, we can prove that we increase time-bounded entropy, but we have low epiplexity. In contrast, as we showed earlier, Shannon entropy is just basically going to be constant. It's not increased by generating these numbers over what we would have just in like the random seed. And polynomial time Kolmogorov complexity will also not be significantly increased. And so you could imagine starting with like a six-sided die and then having some deterministic transformation to some 20-sided die. And with computational constraints, the time-bounded entropy will increase a lot, but the standard entropy will not. We can now also go through each of these paradoxes and understand them both theoretically and empirically using epiplexity and time-bounded entropy. And so here, as we've described briefly earlier, we have data generated by three different ECA rules. So rule 15, which is quite trivial, rule 30, which gives you basically unpredictable structure, and rule 54, which is sophisticated but still predictable given enough computation. In the left panel on the bottom row, we have the time-bounded MDL, so basically the epiplexity plus the time-bounded entropy. Each of these tiny thin curves corresponds to what we get when we do a different set and configuration of hyperparameters. So remember, we're only measuring epiplexity for an optimal model. And so we need like a good configuration of models. So we need to find something on this Pareto frontier. And that will give us the time-bounded entropy under consideration. And so for rule 15, we can see that the time-bounded entropy shoots down very quickly. We have low epiplexity and we have low time-bounded entropy. We can see that the time-bounded MDL for rule 30 in red doesn't really change at all during as we increase computation. And so we have low epiplexity So if you think intuitively about area under the loss curve, about the final value of the loss isn't much different than the initial value. And so that's going to be basically zero. And everything kind of goes into time-bounded entropy for our time-bounded MDL. And then for rule 54, we see this sustained and significant decrease in time-bounded MDL. And so we see an increase in epiplexity as we continue to train and a decrease in time-bounded entropy. So as we expand computation, the data looks less and less random to the model, and it has higher epiplexity. Okay, so this was the first paradox. Information cannot be created deterministically. ECA are simple deterministic rules for evolving data. We do see that time-bounded information does change. Paradox two, information is independent of ordering. So we can show that if we apply these one-way functions, for example, that time-bounded entropy does not satisfy the symmetry of information in theory. So in this instance, going from y to x provides more information than going from x to y if y is given by a one-way function evaluated on X, so something that's very computationally expensive to invert. And this implies that things like data format can change accessible information under computational constraints. You can also do this experiment empirically. And so Rule 30 of ECA is conjectured to be basically a one-way transformation. And so you can try to learn the forward transformation versus the reverse transformation and show that you end up with higher epiplexity and higher time-bounded entropy when you try to learn the reverse. We can also look at systems like chess to get some understanding. So you could imagine some serialization of data where you have chess moves and the configuration of the chess board. And we could either try to predict the board from the moves, or we could try to predict the moves from the board. And intuitively, the latter setting is going to be much harder as a learning problem, and it's going to contain more epiplexity. And so we can actually look at the time-bounded entropy and the epiplexity as a function of computation for the forward and reverse orderings. And so the reverse ordering indeed does have more epiplexity. And once we've trained a model in each of these orders, we can apply them to downstream tasks. And so we find for various out-of-distribution problems like Centipon chess evaluation problems, training on the reverse ordering actually leads to better downstream performance because the model is capturing more interesting structure. Paradox three, that likelihood modeling is just distribution matching. And so a while back, Ilya Sutskever was asked why we should care about next word prediction. And this was before everyone had realized that LLMs actually, well, I still don't know if everyone's realized this, but before most of us had realized that LLMs are actually pretty extraordinary, if limited in some ways, still pretty incredible. And an example he gave was to say that imagine you're reading like a murder mystery book, and the last sentence of the book is the murderer is blank. If the model is able to predict blank with a high degree of accuracy, then seemingly it's understood a lot of what's in the book, and this is meaningfully associated with intelligent behavior. You can actually repurpose this example to also understand induction. So the author, when they wrote the book, probably just chose someone to be the murderer, like Bob's the murderer. And then they planted a bunch of clues in the book that could suggest to the reader that Bob might indeed be the murderer. And so the induction that the reader has to do in figuring out the murderer is very different than the induction that the author did when they generated the data. And so we can construct learning examples like this, where the generative process is not having to really do the same induction as the model. So we could imagine, for instance, having a sequence of just binary numbers, and then we can have a function operating on that sequence to give us some output, and it could be a fairly learnable function. And we also create a copy of the original sequence, and we mask a certain number of bits, and we show the model the mask sequence, and it has to predict the output. And so the model has to infer latent values of these bits, which is not something that needed to happen when we were generating the data. And the more bits that we mask, the higher epiplexity the model actually learns from the data. So it's a harder learning task, but it's able to actually learn something more interesting if we have more missing bits here. We can also return to these ECA to understand things like emergent phenomena and emergent structure. So here we're considering Rule 54, which is that rule that has a fair amount of sophisticated structure, but it's predictable if you have enough compute. Um, and in the space of models that we're searching over, we're including both looped and non-looped transformers. And so loops transformers basically have recurrence cycles in them that allow you to kind of auto-regressively unroll certain types of procedures. And interestingly, we see that beyond a certain threshold of compute, suddenly the looped transformer has much lower time-bounded MDL, so that's epiplexity plus time-bounded entropy, than the non-looped transformer. And so it actually has learned to kind of brute force this problem. And so just stepping back and thinking about ECA again, these are just very simple deterministic rules that describe the evolution of states. And so to get great in distribution generalization, you don't need a very big description length. You just really need to understand what the rules are. But that's very hard from the generated data. So instead, most models are just going to try to exploit emergent structure in what's been generated, so floaters and things like this on the screen, in order to predict a certain number of states ahead. And a very similar sort of reasoning applies to things like AlphaZero. So if you're unbounded in your computation, you can just sort of start with your random seed and the rules of chess and everything else and just evolve that system. And you can say, okay, well, this takes hundreds of millions of TPU hours or something like this, but that's not counted in what's being learned by the model because we don't care about computation and we can just simulate the system. However, in order for the model to learn something useful with computational constraints, it does need to exploit emergent structure. And so this is an instance in which the loop transformer is actually able to brute force the solution, unrolling these ECA states, and its epiplexity actually goes down very significantly beyond a certain threshold of computation. And so this shows a few different things. One of the things it shows is that epiplexity doesn't actually have to be monotonic in computation. So it can actually decrease if you learn to like reverse engineer the generative process for the data. And the resulting representation in this instance might actually be less transferable because, well, it can do good in distribution prediction. It's not learning as much predictable structure, which might be relevant for other sorts of downstream generalization problems. And so that leads us nicely into sort of more real world like applications. And so, as I mentioned, we can think of epiplexity as providing a theory for understanding how to transform select and synthesize data towards particularly out of distribution generalization. Um, and we can use this to understand things like why is language data more transferable than other types of data. And so this was something that we measured on a variety of different modalities of data. And we found that even though time-bounded entropy sort of dominated for each of these modalities, uh, language data had significantly higher epiplexity than many other sources of data, like image data. And we actually looked at this further, as well as like different representations of image data using scaling law assumptions. So another question you might have when it comes to epiplexity in practice is like, are there kind of efficient ways of evaluating epiplexity? So area under the loss curve above the final value of the loss is pretty easy to understand and implement, but sometimes it could be expensive. Depends. I mean, if you're just training your model anyway, then you get epiplexity for free from that. But you can use scaling laws, which apply very well to all different sources of data and they're very well understood to estimate what epiplexity would be from fairly small training runs, at what would happen if you had more compute. So we looked at this sort of area under the loss curve approach to estimate epiplexity and time-bounded entropy for uh, a variety of data sets, language, image, and video with 10 to the 12 tokens and a budget of 10 to the 25 flops, which is comparable to the training compute required for the Llama 370 billion parameter LLM. And again, we find that language data had highest epiplexity, image data had the least. Special tokenizations of images increased epiplexity. Video generally had pretty low epiplexity and time-bounded entropy relative to image data with the same resolution because there is likely a lot of redundancy along the temporal dimension. We can also look at asymptotics for epiplexity using these scaling laws. And so according to the scaling laws, you would generally increase epiplexity as you increase compute, and the amount of data that you're using would approach the size of the full data set you have available to you. There are these parameters that influence these scaling laws. So if you have smaller beta and larger D naught in this instance, you'll get higher epiplexity. We did see, though, that this isn't, always the case. Sometimes beyond a certain threshold of compute, you could actually just reverse engineer the generative process for the data and your epiplexity could shoot down. But we would conjecture that this doesn't happen in most cases for any realistic amount of compute that you would be expending on most problems. Just as like a footnote, for this first experiment I mentioned in panel A on this slide, we were using the sequential coding procedure, which provides a higher fidelity measurement of epiplexity than the area under the loss curve approach. We can also use epiplexity for online and curriculum learning. And so it's really of great interest to understand how you can train your model on mixtures of data drawn from different distributions. A lot of reasoning in this space relies on very hand-wavy notions of quality and diversity. Epiplexity allows you to formalize some of those notions. Also, standard evaluation of perplexity on held out data sets can be susceptible to data contamination. It can overfit to very specific tasks and so on. And so this also provides us with a motivation for trying to measure something else as well, like epiplexity, which can transfer more broadly. So remember, epiplexity here, when we're thinking about downstream generalization, is particularly relevant when we don't know what data we're going to be predicting on downstream. And this is increasingly the case. And so you can't just say, okay, well, I'm just going to measure validation loss, and maybe that's better than epiplexity for what I care about. Well, quite often you don't necessarily know what you're going to care about. So we trained a 1.3 billion parameter decoder only transformer on 125 billion tokens from something called the pile dataset, which has sort of a variety of different data sources. And we evaluate on 7 zero-shot downstream tasks and 2 out-of-distribution tasks, fine web and slim pajama. And we can show that procedures that are selecting higher epiplexity data, like the ADO curriculum learning procedure, will generalize much better on these downstream tasks and for OD prediction problems, even though they have higher training loss. And so this actually is something that corresponds better to downstream generalization than training loss. So in short, we can incorporate an understanding of computation, and we can target useful information content to try to resolve the tension between what seems to be suggested by information theory and learning theory and what we observe in modern AI practice around the value of synthetic data, of course, pseudo-random numbers, which isn't just modern AI practice, the importance of ordering, and emergent phenomena. And we can use this measure of information that we proposed, epiplexity, which stands for epistemic complexity, to reason about these paradoxes and also provide a foundation for data selection and thinking about synthetic data. All right, thank you.
All right, thank you, Andrew. Should we switched